Okay, we'll start it. I have got only two people. It's all right. So we were talking about electrophilic substitutions yesterday. Electrophilic aromatic substitutions. Okay, we'll just talk about uh, nitration. Nitration we have. I just wanted to give you the mechanism of sulfonation. Okay, first of all, sulfuric acid. This is the structure of complete structure of sulfuric acid. OH, S double bond O, double bond O, OH. Okay. Now this is reacted with one more mole of sulfuric acid, H, O, S double bond O, double bond O, OH. So one molecule of sulfuric acid will act as an acid and the other will be acting as a nucleophile, electrophile. You are going to generate an electrophile from the other. So this is going to act as a base. How does it act? See here, you can take either this lone pair of electron or maybe this lone pair of electron. So what I think is you can take this lone pair of electron and attack this. This pair of electron will come to the oxygen that gives you H SO4 minus. Okay, HSO4 minus, and this will become O, one H here with a positive charge here, S double bond O, double bond O, and OH. Now this acts as a very good leaving group. See here, why does it act as a leaving group? Because it is going to be water which is going out. So these two electrons will be, and that will be, see here, and see what happens. This HSO4 minus will abstract this proton. So what do you get? H2O is separated from the other side plus SO3, sulfur trioxide, plus H2SO4. So now your sulfur trioxide is the electrophile. Now why is sulfur trioxide an electrophile? You have, it is, see here, 6 bonds, okay, delta plus, 3 delta plus, plus plus. Why plus plus plus? Because this is delta minus, this is delta minus, this is delta minus. Why it is delta minus? More electronegative. More electronegative. Oxygen is more electronegative, therefore sulfur is highly deficient of electron. It attracts this pair of electrons towards oxygen. Okay, so 6 pairs of electrons are attracted towards the oxygen, and that makes it a very strong nuclear electrophile. Now you have your benzene ring. We have the benzene ring, and see here, writing the mechanism of this reaction. We have SO3 neutral nucleophile, neutral electrophile. Remember that it's neutral. Now this shifts over here and this shifts over here. At any time, sulfur should have 6 bonds only. Now you have, see here, 1, 2, and S double bond O, double bond O, O minus. And where is the plus? The plus is here, because it is this bond which has come here. So this carbon has lost a bond. This carbon has lost a bond, lost an electron. So it gets a plus charge. Now, you can resonate this one. The plus comes here. You can write it separately. Please write it separately. You can bring this here. And here also it becomes positive. Okay. Now loss of proton. Next step. See, this is the first step. Generation of electrophile. Electrophile. Generated. And second, pi complex formation and sigma complex. Pi and sigma complexes. Pi complex I have told you yesterday. Before this is formed, see here. You have an SO3. The whole cloud is coming here. That is pi complex. Then it comes here, sigma complex. So this is sigma complex. And now loss of proton. See here. This is loss of proton. Write it separately. Write this as separate figures. Okay. Now this gives you the product by regaining the aromaticity SO3 minus. And now you react this with water. No, not with water. Yeah, plus H plus. H plus. And H plus catches here and form. What does it form? It forms the product. Pyratoluene sulfonic acid. SO3H. So this is a sulfonation reaction. Mechanism of sulfonation. Now we have Fourier-Graph reactions. Fourier-Graph reactions. Benzene treated with methyl chloride. That gives you toluene in presence of aluminum chloride as a catalyst in catalytic amount. That is 5%, 5 more percent is required, that's all. Okay. And if you take you can write the mechanism as such. One second. This is reacted with Cl. What product you will get? Remove the Cl and connect it. My hands are paining. That is why my writing is not very good. Too much of use of this board has given me a lot of problems. Okay. Now, so this is isopropyl group being attached. Okay. Suppose you have this one. What do you do? Cut here and attach it. Okay. But there is one thing you have to remember. If you take this and take this compound, 1, 2, 3, 4, you would like to write this product. 1, 2, 3, 4. But actually, this does not form. This is a minor product. This is a minor product. Why? Because the mechanism is first this and this will react to form the electrophile. How does it form? CH3 Cl plus AlCl3 Cl Cl and Cl. See this bond. Aluminum is electron deficient Lewis acid. So this will form CH3 plus the carbocation. AlCl4 minus. This is the same mechanism of halogenation which we have seen yesterday. Very similar mechanism as halogenation. Then, now it is this which is going to react. But we have already studied carbocation primary is very unstable. Unstable. As far as methyl is concerned, no problem. Nothing is going to happen to it. As far as ethyl is concerned, CH3, CH2 also, no problem. No, nothing will going to happen. But as you increase one more carbon, CH3, CH2, CH2 plus. What happens is this is a primary carbocation with alpha hydrogen. Now this alpha hydrogen, this will migrate. We have studied carbocation rearrangement. So this will give CH3, CH3 plus. Okay. So this is a secondary carbocation. Are you able to follow? So this secondary carbocation will react with benzene and will form this product and not this product. That is why you have seen a trick here. See this? They have not given, your textbook does not give you this compound. This is the reason. Even if you take this, you'll get only this product plus the minor product of other. This is going to be a minor product. 1, 2, 3. This is minor. This is major product. Why? Carbocation rearrangement is the answer. Suppose instead of this I have got one more carbon. 1, 2, 3, 4. This one, which we have already seen. Not this, yeah. Yeah. Look at this one. It will form this carbocation. See. 1, 2, 3, 4 plus. Now we have NH here. This will go here. What will you get? You will get a secondary carbocation. Okay, you will get a secondary carbocation. Is there a chance for this to form a tertiary carbocation? Is there any chance for this to form a tertiary carbocation? Why don't we try? For that purpose, some methyl has to come here. Let us see. Can this come here and see? It will form CH3, CH2 plus. There is one hydrogen here. Ah, yeah. Let's see. CH3 plus, CH2 plus. Yes. CH3 and CH3. Okay. This again become a secondary carbocation. Sorry, primary carbocation. Even though you have a tertiary carbon in the center. Now see what happens. This migrates. What does it form? It forms a tertiary carbocation. So what is the product? I'll rewrite the whole stuff. You'll get confused with whatever I have told. I'll rewrite one second. Look here, this is what we are trying to convey. This reacting with 1, 2, 3, 4 Cl. Cl. In presence of aluminum chloride. Now 1, 2, 3, 4 plus AlCl4 minus. This is the nuclear electrophile. This is a primary carbocation. Look at the rearrangement occurring. This H along with the pair of electron will migrate here and will form 1, 2, 3, 4. So this is primary. Primary I can write as, look here, easy way. First degree. This one, second degree, means secondary. Secondary. Now, this will migrate here. Again, you will end up with the primary, but this is a more stabilized carbocation because you have two methyl group, which is more powerful here. And now see here, this migrates. What will you get? Oh, sorry. You will get a tertiary carbocation. So what is the product from here? The product is a mixture of 1, 2, 3, 4 minor products plus 1, 2, 3 okay from this. Plus you will get 1, 2, 3. So this product. What's the major product? This is the major product. You understood? So this is the drawback of Friedrich-Kapp alkylation reaction. What is the drawback? That is, it undergoes rearrangement and multiple products are obtained. Since it involved a carbocation, primary carbocations will undergo rearrangement into secondary, into tertiary, and that will lead to formation of multiple products, which is never favorable. Let us look at the next type of reaction, that is Friedrich-Kapp acylation reaction. Plus acid chloride, CH3COCl, in presence of aluminum chloride. How do you get COCl? CS3, COOH. You take an acid and react with SOCl2. You'll get acid chloride. Now here you can write the mechanism in the same fashion. You will get CS3, C double bond O with a positive charge. This can be resonance stabilized. See here. There are two lone pair of electrons. And this is what is called as helium ion. Positive charge on the oxygen. Okay. Now we have benzene ring. You can do this way, or you can write here. Same thing. You get the same result. What do you get? Positive charge. Now do the remaining things and remove the proton from here, ultimately. That is the mechanism of periodic acylation reaction. Now remember, you can take any acid chloride, CS3, see here. I can take this. Okay, now this will form CS3, 1, 2, 3, 4, 5, 6. A helium ion. Remember, no rearrangement. No rearrangement occurred. So you get only one product. You get only one product. So if you are asked to synthesize this compound, see here, 1, 2, 3, 4. We want to synthesize this compound. If you go by this method, you will end up with this, all these things. 4 products. Okay, what we will do? We will take the ketone of this. We will prepare the ketone first. We will react with, see here, Cl, CO. So 1, 2, 3, 4. Aluminum chloride, AlCl3. You will get a ketone. 1, 2, 3, 4. Now ketone can be reduced into CH2. CO can be converted into CH2 by 2 reactions. One, Clemmensen reduction. Clemmensen reduction. Or Wolff-Kishner reduction. So you get only one product, no mixture. So these are the importance of acylation reaction. Okay. Next, dye substitution or multi-substitution. Let us look at the effect of a group on benzene ring, how it influences further chemical electrophilic reactions. Example, I take phenol. do a bromination. I get 1, 2, 3. A tri-bromo product. Very easy reaction. Very easy. You take this aniline also. Instead of OH, you take NH2. Same reaction. Only difference is instead of OH, you have NH2. One minute. Okay, I don't want to bring confusion to you by putting the NH2 in a different place. Actually, it makes no difference, I know, but still. Yeah. See here. The OH and NH2 has activated the benzene ring so much that 3 places are brominated. So very highly reactive. Very, very highly reactive. Suppose you want to brominate only one place, you have to make some other method. Now, look at this one. I got toluene. React with CH3Cl, AlCl3. I get this plus para product. So you call CH3 as ortho-para directing. CH3 as ortho-para directing. Now you take a Cl. Do a nitration. HNO3. Sulfuric acid. H2SO4. Sorry. H2SO4. Giving you ortho nitro plus plus Cl here and NO2 here. Okay. So all these groups, NO2, OH, Cl, CH3, all these are electron donating groups, EDC. EDC. Instead of this, look at this one. And do the reaction, like do a nitration. HNO3 sulfuric acid. HNO3 sulfuric acid. Okay. What will you get? You get a meta product. You get a meta product. Now, how do you know whether a group is electron withdrawing or electron donating? So these are electron withdrawing groups. How do you know whether a group is electron donating or electron withdrawing? We have already mentioned it. Look at the atom attached to the ring. If the atom contains a lone pair, if the atom attached to the benzene ring contains a lone pair, it is going to be electron donating. If it carries a partial positive charge, if it carries a partial positive charge or a full positive charge, it is electron withdrawing. Simple. Now look at this one, benzoic acid. C double bond O, OH. See that? Yeah, this is delta negative. This is also a delta negative. Delta positive. See here. So meta directing. Meta directing. So this is how you see sulfonic acid. SO3H. Again the same way. Draw the complete structure. Find out S double bond O, double bond O, OH. See that? Delta plus, delta plus plus plus, ID meta directing. Okay. So ortho para directing and meta directing groups. You have to write the resonance structures, don't forget it. When you explain the meta directing and ortho para directing, you can ask it, they can ask you a question, always many times it comes. Explain. Why? NO2 and SO3H are meta directing. While NH2 OCS3 are ortho para directing. Many times they ask an essay like this, a short essay, maybe half of this or full of this, whatever it is that. You have to write the resonance structures. And also you give examples. Write the resonance structures by putting NO2, putting SO3H, and give examples. So this is the electrophilic substitutions of benzene ring. Now what we have to look into is what is called aromaticity. Something which is known as aromaticity. Let me clear the board first. I'll remove the board. Aromaticity. Okay. See, let us characterize the properties of benzene. Okay. Benzene is cyclic. It's conjugated. Okay. Benzene is cyclic, conjugated, sp2 carbons. sp2 carbon, and each carbon is containing a p orbital. Each carbon is containing a p orbital. P orbital. Second characteristic of benzene, then does not undergo no addition reaction. Rarely addition reaction occurs. substitution reaction. We have seen that. Electrophilic substitution, chlorine substituting, NO2 substituting, SO3H substituting, CH3 substituting, CH3CO substituting. All these are substitution reactions. The benzene ring double bond not getting affected. Number 3, it undergoes substitution reaction as we have already mentioned. Yeah. Okay. Number 4, the heat of hydrogenation. The heat of hydrogenation is different from that is calculated from double bonded compounds. The heat of hydrogenation is different from that is calculated from the double bonded, triple bonded compounds. Three double bonded compounds. So the calculated value and the actual value of hydrogenation is different. This difference in energy is known as resonance energy or delocalization energy. Okay, it is called delocalization energy. Now, there are many other compounds having the same properties, and these compounds are highly stable. They are very highly stable than expected from similar compounds. So this stability is known as aromaticity. Okay, this stability is known as aromaticity. Now let us define the aromatic character as a compound is aromatic, or aromatic character is shown by compounds with the following characteristics. Number 1, planar. Number 2, cyclic compounds. Planar, cyclic. Number 3, each atom contains a p orbital. Each atom in the ring, in the cyclic ring, with a p orbital. And number 4, they contain four n+2 pi electrons. Let us apply this to benzene. Where I had to fill it here, where n is an integer, not a fraction. 0 to n. In 0